Whether it's sending space probes beyond the edge of our solar system or one day landing astronauts on Mars, mankind has forever been fascinated with the study of the heavens. But such exploration is not easy. So we came here to NASA's Glenn Research Facility to get a first-hand look of the advancements being made today that will power the spacecraft of tomorrow. So now we're down in the Sterling Research Lab at NASA's Glenn Research Center. I'm talking to Lee Mason, and he's showing us one of his experimental setups. Lee, can you tell us a little bit about what we're looking at here?
Yes, this is a pair of free-piston Stirling converters. They're being developed as the power generation portion of an advanced Stirling radioisotope generator. And ASRGs are a potential power source for deep space planetary missions.
So you mentioned radioisotopes as the heat source. Can you explain a little bit about that process?
So radioisotope is a nuclear heat source, and what we do is we use the natural decay of plutonium-238 to generate heat that can be converted into electricity.
So are you actually using plutonium-238 in these test stands?
No, none of the testing we do at Glenn Research Center involves nuclear materials. What we do is we simulate those nuclear materials with electrical heaters that provide the same type of interface that the nuclear materials would provide.
So you've mentioned that these are power sources, and traditionally when we think of power sources for spacecraft, we think of big thrusting engines. Can you tell us a little bit about how these power sources would be used on the spacecraft?
Yes, so these are for generating electrical power, and anytime you send a deep space probe out, you need a power source for the instruments that are on board. So this would provide the electrical power to run those instruments and also to communicate the information back to Earth.
Could these Stirling engines ever be used to produce any propulsion in these systems?
Well, if you scale these systems up to much larger sizes, they might be considered as a power source for ion propulsion, which would provide the thrust to allow rockets to move in space.
How much power do these engines produce?
These units generate about 80 watts each. So they are designed to operate as a pair to produce 160 watts, which doesn't sound like a lot of power, but it's plenty of power for the type of instruments that would be used on deep space planetary missions.
What kind of specific testing are you doing with these Stirling engines we're looking at here?
One of the key purposes of this Sterling Research Lab at Glenn Research Center is to generate the life and reliability data to prove that this technology can be used for deep space missions that may last 20 years. So one of our objectives is to put these engines on life testing and let them run continuously on a 24-hour, 7-day-a-week basis. So these engines have been operating since January and have accumulated something on the order of 1,600 hours each. But all told, we've run probably 40 Stirling converters in this lab, accumulating over 500,000 hours of operational data.
So do you try to operate these engines under similar conditions they would actually experience during the mission, or do you try to overload them to do any failure testing?
We do a number of different tests. When they are on their continuous extended operational life testing, they're operated at a constant point. But we also do a number of tests to test how well they can operate over a wide range of conditions. And so we do what's called performance mapping. So we'll operate them at low power and low temperature, or high power and high temperature, just to prove that they can operate over those ranges.
Can you walk us through step by step how these engines actually operate?
Yes. A free piston Stirling engine has two moving parts. It has a displacer that oscillates in the heat engine portion, and it has a piston that oscillates in the alternator portion. And the displacer produces forces that act on the piston, which causes a motion, and from that motion you can extract electrical power through a series of field windings that surround the piston.
Can you describe how the plutonium-238 actually provides the energy you need to power these sources?
So the plutonium heat source, which we simulate here, produces heat that's conducted through the engine housing. And that heat causes a gas inside the engine to expand, which causes the displacer to move. And that force that's introduced causes the displacer to oscillate by a cyclic heating and cooling of the working fluid.
Could you give us a general idea of the types of missions that these power sources would be used for? And are there any current missions being planned that would utilize this technology?
These would be best suited for planetary science missions. There were a couple of missions that were being considered as part of NASA's Discovery mission program. One of the missions was going to use a system like this to go to Titan and land on one of the methane lakes at Titan and explore the chemistry there. Another mission was being considered that would use a system like this to rendezvous with a comet and do multiple hops on that comet. It was called the Chopper mission. And that would have done elemental science at each of those locations on this comet as it proceeds towards the sun.
So what are the advantages of the Stirling engine design compared to some of the other power generation systems that have been used previously?
What we're trying to do here is develop a high efficiency power conversion system to replace the traditional system, which is called thermoelectrics. And thermoelectrics have been used in space for over 50 years to convert nuclear heat into electricity and have done it very reliably, but it's only about 5% efficient. The Stirling engines are about 25 to 30% efficient, and therefore they use a lot less nuclear fuel. And that's really important today because we don't have a lot of the nuclear fuel to power these systems. So we're trying to take advantage of the small amount we have and convert it most efficiently.
Obviously, plutonium-238 is a scarce resource. Are there any efforts now to begin producing more plutonium-238 for this type of application?
Yes, so the U.S. is about to begin production of plutonium-238 domestically, which we haven't done since the Clinton administration. So it's been a long time since we've produced plutonium-238 here. So we've had to buy it from other international sources. So now that we're producing it again, we expect that systems like this could be utilized for a lot of different space science missions.
When do you expect this specific design to be deployed by a NASA mission?
So we are working towards our first flight system. In fact, these engines are the final engineering models that have been developed. We are in the process now of building the flight components, which will be assembled with the hopes of completing a flight generator by 2016.
So in the Stirling engine test facility we were in previously, the experiments were set up on simple test stands. But now we're in another facility that is quite a bit more grand. Lee, can you tell us a little bit about where we're standing right now?
Yes, so downstairs in the Stirling Research Lab, it's perfectly good to mount the engines on ambient test stands in air because we're about collecting life data and long-term reliability data. But in a facility like this, we're more interested in how the systems respond to the actual space operating environment. So big vacuum chambers like this are used to simulate that environment.
Can you tell us a little bit about the history of this facility and how it operates?
This facility is called Vacuum Facility Number 6, or Tank 6. It was built back in the 1950s by some very smart people who knew enough about what was coming for NASA and space exploration to generate these kinds of test environments to allow us to test systems here on the ground before we launch them into space.
How does this facility achieve the near zero pressure environment of space?
There's a number of aspects to the facility. First of all, it does simulate the vacuum or lack of pressure or air pressure in space using big pumps to pump away the air. It also includes a couple of other features that make it very useful for testing space systems. It includes a wall around the entire circumference that has liquid nitrogen that flows through it to simulate the temperatures that we would see in space.
Can you give us an idea of the size and scale of this facility?
This facility was built to test big systems. It's about 60 feet long and about 25 feet in diameter. And so we're able to accommodate very large structures. The big end door is on a rail system that allows it to move and close, but there's a system that allows large structures to be placed on that rail and rolled into the chamber. And the importance of having a big volume is that a lot of these space systems need that space to demonstrate their functionality in a real space-like environment.
We are often captivated by some of the impressive numbers that these facilities can achieve. Can you give us a rundown of some of this experiment's highlights?
Yes, this is a world-class facility. It can simulate the conditions of space like very few other facilities in all the world. For example, it can pump the air out of this chamber in less than 24 hours and provide a vacuum of 10 to the minus 7 torr. That's a measure of how much pressure is in there. And actually it includes a third element. It includes what we call a solar simulator, where we can simulate the sunlight that would be available for systems that orbit Earth in space to simulate the amount of sunlight that they would see. So it can simulate sunlight, vacuum, and temperature all in one facility.
What other types of experiments have been conducted here in the past?
So the facilities were built back in the 1950s, and their primary purpose at that time was to develop electric propulsion technology. And in fact, electric propulsion technology was invented at NASA Glenn. Then it was called Lewis Research Center. But these facilities were built to test ion thrusters and provide the proper environment to test those thrusters in conditions that they would see up in space.
What other types of experiments could you see being conducted here in the future?
There's kind of two purposes to the facility. In the current test or experiment that we're doing is more about technology development, developing a first-of-a-kind system to prove that it works. But facilities like this are also utilized to do acceptance testing of real spaceflight hardware.
So earlier we were looking at applications of Stirling motors to small space probes. But what if you needed more power? What if you were looking to set up a civilization, say, on Mars? How would you go about doing that? To explore that and what NASA is doing to begin answering these questions, I'm talking here with Mark Gibson. Mark, can you give us a little bit of background on the experiment we're looking at here?
Sure. What you're looking at is a 40 kilowatt system that we have demonstration for the Moon and Mars. And what you're looking at is the upper truss structure, which is going to house 4 of the engines, as well as the coolant system and some of the heat rejection that goes into the system.
This is obviously still under construction, so what pieces are missing here?
The pieces that are missing there are the engines. There's a pair of 6 kilowatt Stirling engines that go in this assembly, so that's 6,000 watts each. They are in the dual opposed configuration, providing 12,000 watts. So this is a quarter scale power, full scale geometric test that we do to try and better understand what the conditions are going to be in space and how the system is going to react while in that environment.
So how do these engines differ from the ones we saw previously?
Obviously they're bigger, so you're going from a couple hundred watts up to 12,000 watts. So size-wise, they're about 4 foot long and 10 or 12 inches in diameter. So size-wise, they scale up quite a bit.
In the smaller Stirling engines we saw previously, they used plutonium-238 as the main heat source. What do you use in the larger Stirling engines?
The plutonium radioisotope system works off of the decay heat from the nuclear source. This is using uranium-235, which is a fissionable material, and so we use that fission heat to power the Stirlings through a heat transfer process where we use liquid metal coolant that we pump through the core that goes around the fuel, picks up the heat, and then takes it up to the Stirling engines, and then the Stirling engines accept that heat and where they can turn it into electricity. So it's a pump loop fission process versus a conduction radioisotope process.
In this experiment, you're not actually using uranium-235 though. What are you using to simulate that?
Or use graphite pen heaters, which are resistance electrical heaters that provide the heat, and we power them through a number of different ways to try to simulate the exact response that we would get from a nuclear heat source.
The discoveries being made here today will lay the foundation for the next generation of planetary explorers, and perhaps even power a manned mission to Mars. Join us next time as we take a closer look at the aerogel technology being developed here at NASA's Glenn Research Center, which has the potential to impact everything from spacecraft design to the efficiency of your house, all on tomorrow's discoveries.